In the previous video, we established one important fact. As sample sizes vary, so does the size of the sampling error. In fact, what that simply says is that if from a whole population we draw different samples, the information we will get from the different samples will vary. So the question remains, which of the samples or which information piece from the different samples should we trust? Which should be our final estimate of the entire population characteristic? To answer that question, in statistics, we adopt a technique called repeated sampling. So, in repeated sampling, we first decide to pick a large enough sample. So on your screen, I'm choosing large enough sample, which would necessitate asking the question, what number indicates a sample size that is large enough in statistics? Then, after deciding which sample is large enough or what size of a sample is large enough, we would also decide how many times we want to repeat these samples that we're going to be choosing. So we're going to let M represent the number of times we will repeatedly sample data values from the entire population. To answer the question we asked earlier, what size of a sample is large enough, we always, in statistics, at this introductory level, consider a sample size of size 30 to be a large enough sample. Now, we might ask, why is it important, to consider how large enough our sample is? It is because whenever we draw sample data values, we want them to give us data values that give as accurate or precise as possible an information to represent the entire population characteristic. So, in order to ensure that we get a better estimate of the population characteristic, choosing a large enough sample is important. So also is conducting repeated sampling. Well, with repeated sampling, we're going to generate a host of different data values. And by extension, when we generate a host of data values, we will be able to graph them just as we would any basic numerical variable. So let's see what that involves. That will involve going down into the nitty-gritties of this topic, namely the sampling distribution of the sample mean. In order to fully grasp this idea, I will take you back memory lane. Do you remember the distribution that has this shape? It is called the normal distribution. So let's say we start off with X, a variable of interest that has the normal distribution. That will mean that it can be described by its mean, which will be its most popular value, and then we'll consider how other values spread away from the mean by measuring it using the standard deviation. So if X has the normal distribution, we usually summarize that as X following the normal distribution with a mean of mu and a standard deviation of sigma. If from this distribution of data values, I choose a sample, the first sample, let's say a large enough or even not large enough sample, just a sample, and I calculate the sample mean, I will get sample mean 1. Then if I choose another set of sample data values, possibly after replacing the initial data values I chose, then I will get another sample mean, which I will call sample mean 2. If I repeat this process 1,000 times, it means I will have 1,000 sample means. Well, I can draw a histogram of all the 1,000 sample means. And what we have found out in research is that if I drew the histogram, I will always end up with, again, another normal distribution for all the possible sample means that I can get. And this sample mean X bar will also have a normal population or a normal distribution as depicted in this picture. Its mean, it will share exactly the same mean as the parent distribution, so it will have exactly the same mean. However, its standard deviation would differ. It will be the parent standard deviation divided by the square root of the sample size. What does this mean for our calculations in this class? Let us see on the next page. On the next page, we're going to start off gently. We'll consider some examples where we'll learn about the mean of the sampling distribution of the sample means and the standard deviation of the sampling distribution of the sample means. This is otherwise called the standard error of the mean. So, let's just see what this involves. In this example, we are to suppose that the movie ticket prices in one area has a mean of $18.32. So the mean is $18.32 and a standard deviation of 0.72. Ticket prices are recorded for samples of size 52. We have to calculate the mean of the resulting sampling distribution. What does this mean? It means that if we go back to the parent distribution, this distribution is considered the parent distribution that gave birth to this derived or sampling distribution of the sample mean. Well, if it has a normal distribution, it must have a mean, just like the parent distribution had a mean. What we found out is that they always share the same mean. In other words, in this question, since we were given the original mean, the mean of the sampling distribution, which is mean of X bar, is exactly equal to the original parent mean. No calculations necessary. It is equal to 8.32. With that said, let us see, for the same context, the same language of the same question, this time, rather than computing the mean of the sampling distribution, we would like to compute the standard deviation of the sampling distribution. This, again, is otherwise called the standard error of the sampling distribution. And we can represent that as sigma of X bar. This is always equal to, as this formula shows, the parent standard deviation divided by the square root of the sample size. That will be equal to, what is the standard deviation of the parent distribution? 0.72 divided by the square root of the sample size. What was the sample size chosen? Samples of 52 theaters. So you have 52 here. And this will be equal to 0.0998. So in this example, we have illustrated a quick basic example of what we are talking about here. In other words, if we know this distribution, we can always derive the values here. So, without any further ado, let's proceed to more interesting examples on page 10. In this question, we are told that a normally distributed population has a mean of 500 and a standard deviation of 60. So what that means is that there is a parent distribution here. The parent distribution has a normal distribution with a mean of 500 in the middle and a standard deviation of 60. Well, this question would, to begin with, like us to determine the probability that a random sample of size 16 selected from this population will have a sample mean less than 475. For the sake of emphasis, I am going to read this question again. We're to determine the probability that a given random sample of size 16, so my n in this case is 16, selected from this population. What population is that? This population will have a sample mean, that is x bar, less than 475. So based on the requirements of the question, I would like to compute probability P that x bar is less than 475. How is this different from what we learned in module 6? Well, first of all, this probability is concerned or connected to the sample mean, not just ordinary x. So in this case, the first part of this problem, or the first way to solve this problem, is to derive the sampling distribution of the sample mean, which, since we're starting off with a normal distribution or a normal population, we know that the resulting distribution x bar will also be normal. However, they will share the same mean. The mean of x bar will still be 500, but the standard error of x bar will be the parent standard deviation, which is sigma divided by the square root of n. So that will be 60 divided by the square root of 16. That's 60 divided by 4, which is equal to 15. So now that we have the parameters, the two parameters of this normal distribution that is connected to the sample mean, we can now answer this question. And to answer that question, this is what I'll do. I will locate 475. That will be a number before 500. So 475. And I'm interested in the probability below, that is to the left, of 475. That is right here. And since this is connected to the normal distribution, I will use the normal distribution calculator. So I'm going to go and start off the online normal calculator. And here it is on my screen. I'll need to key in the mean. The mean in this case is 500. Take note, I am not using this distribution. I must first derive the distribution of the sample mean first. I have it here. The mean is 500, but the standard error or standard deviation is 15, not 60. Again, it is 15, not 60. So 500 and 15 goes to the normal calculator. So I have 515, and then I'm interested in the probability connected with or below 475. So going back, I will do this. Let's go to below 475 and enter. So I have 0.0478. So I have an answer here. The answer is 0.0478. This is the probability that the sample mean is less than 475. Then, for question B, we are to determine the probability that a random sample of size 25 this time. So my n has changed to 25. Selected from the population will have a sample mean greater than or equal to 515. These are the highlights. Probability, I'm going to write equal to P, that the sample mean, that will be x bar, is greater than or equal to 515. So I can write greater than or equal to 515. So in this case, again, since this is connected to this probability is about the sample mean, I will need to derive the sampling distribution of the sample mean. So in this case, for x bar, I would like the mean of x bar. From what I learned earlier, the mean of x bar will always be the same as the parent mean, which is equal to 500. However, the standard deviation of the sampling distribution, or the standard error, will be the population standard deviation divided by the square root of the sample size. That will be equal to 60 divided by the square root of 25, and that will be equal to 12. These two values are what I'm going to need in my calculator. But then, before I do just that, I need to locate where 515 is. This should be 515 somewhere here, above 500, and I'm interested in the area above 515. So that will be the area to the right of 515. And with that, I can go to my normal calculator. The mean is 500, but the standard deviation or standard error has reduced to 12. And I am interested in the area above 515. So going back, so I'm going to click on above 515 and enter. And I have 0.1056. So back to work. My answer here, the probability is 0.1056.